So as promised, we're going to keep finding solutions to exponential equations. Notice that now our base is e. But that's actually kind of convenient. I have the same base on both sides. Unfortunately, I do have to resolve this 1 over e to the 6th because I don't have, what I want is just e to something equals e to something and have that be it. So I need a single expression on the right-hand side. So I'm going to call that e to the minus 6th because then I can combine the two exponents using their sum, 5x plus negative 6. So now my right-hand side is just e to the 5x minus 6. So I'm going to use that, and now I can just say the exponents are equal. So now how would I find an x that solves this? Well, now we're back in like chapter 1 or even 2 material. I just have a degree 2 polynomial, and to find roots, I'm going to use the, I'm either going to factor it, or if I can't, I'll use the quadratic formula. This one can be factored as x plus 6 times x minus 1, which means the solutions are negative 6 or 1. So there were two solutions to this one. Okay, so here's the final example. It's a word problem. Between 9 and 10 p.m., cars arrive at Burger King's. I wonder if they got product placement money for that. I hope not, but I wouldn't put it past them. Anyway, cars arrive at BK's drive-thru at the rate of 15 cars per hour. The following formula, and this is a genuine statistical formula, can be used to determine the probability that a car will arrive within a certain time. So within a certain time length t from 9 p.m., the probability of a car arriving is 1 minus e to the negative 0.25t. The 0.25 here is exactly the 0.25 from the average rate that they're arriving. Okay, but whatever, this formula, just take it, it's been given. Determine the probability a car will arrive within 5 minutes. Determine the probability a car will arrive within 30 minutes, graph the function, and what happens as t gets bigger and bigger. So try to do this. For part A, what is the time? 9:05 p.m. What does that mean in terms of the variable t? How many minutes from 9 is that? It's 5 minutes. All you have to do is plug in t equals 5. So if you plug in t equals 5, it's about 0.71. The probability of a car arriving within 5 minutes is about 71%. Okay, they arrive at a rate of 15 per hour. No, sorry. What was it? 15 cars per hour, right. So on average, they're arriving at a rate of 1 every 4 minutes. So if I wait 5 minutes, I'm 71% likely to have seen a car. What if I wait 30 minutes? Well, on average, they're arriving every 4 minutes. So I think this is going to be very, very likely. It is quite likely that within 30 minutes, a car will have showed up. Well, we just plug in t equals 30, and we get 99.94%. Yes, it is very, very likely a car has showed up. So what happens when we graph this? It looks like that. That's just plugging it into the calculator and setting your window appropriately. Notice that you want y to go from 0 to 1. And you want t to go from 0 to at least 30. Okay, because we did compute 30 in the previous one. So what's happening as t gets bigger and bigger and bigger? What's happening to y? Well, as t gets bigger and bigger, the probability that a car arrives can only increase. I can't have it somehow less likely to have a car arrive within 10 minutes than it was likely to arrive within 5 minutes. Because every car that arrives in minutes also arrives within 10 minutes. So the probability of arriving within a certain length of time can only go up. And what does it go up towards? 100% or 1. Okay. So as t goes to infinity, this bit here goes to 0 because it's an exponential thing with a negative exponent, or you could write this as 1 over e to the 0.25t. You could write it as an exponential function with a positive exponent, but with a base that's less than 1. Typically, we don't do this. We would usually write it in this form. But that part goes to 0, which means my function, which was 1 minus that, goes to 1, which is 100%. So as you let the clock just run on forever, the probability of a car arriving at Burger King eventually approaches 100%. Okay, so that's the end of this section. That last word problem may have hinted to us there's a lot of applications involving exponential functions, and there are many variant ones, and we'll spend a lot of time in this chapter discussing those.